Okay, good afternoon again, everyone. I am Shao Shuo from Zhejiang University. I'm excited to present our work named Explanation as a Watermark, a novel approach about model copyright protection. Let's start with the background. Deep neural networks has been widely applied to various domains, from face recognition and chatbots to self-driving vehicles and weather forecasting. However, training high-performance deep neural networks is a non-trivial thing. It is costly and resource-intensive work, needs large-scale data sets and many computational resources. In the meanwhile, the high-value deep neural networks also face a range of copyright infringements, such as unauthorized commerce and file inversion or illegal redistribution. Deep neural networks should be regarded as an important intellectual property of its developer. This raises an important question. How can we protect the copyright of deep neural networks? Model watermarking has emerged as a critical and widely adopted solution for model copyright protection. It first embeds a developer-specific watermark into the signature into the model. Then, if a similar watermark can be extracted from other parties' model, this model can be regarded as a stolen model. In general, there are two main types of model watermarking methods: white box model watermarking and black box. White box model watermarking directly embed the watermark into the parameters. So it needs the full access to the parameters and the model architectures during the verification. So it may be difficult to accomplish in real-world scenario, since the model are usually deployed as an API. On the other hand, black box watermarking is more flexible and only requires the predictions of the model. Most existing black box methods are based on backdoor attacks. The backdoor model will predict wrong labels when a specific pattern appears. This misclassification behavior can be regarded as a watermark, since the backdoor is secret and only the developer knows it and can extract it and trigger it. However, backdoor-based watermarks suffer from two significant limitations, including harmfulness and ambiguity. First, backdoor-based methods inject patterns that can trigger misclassification. The misclassification is harmful and might be exploited by any adversary. Second, backdoor-based watermarks can be easily forged by adversaries, since misclassification is common in deep learning. Misclassified samples are easy to find, for example, through adversarial example techniques. We find that such limitations stem from the zero-bit nature of backdoor watermarks. That's to say, a zero-bit watermark can only detect the presence and the absence of the watermark without any extra information. It's quite easy to forge. Additionally, the backdoor watermarks depend on changing the predictions, therefore leading to harmfulness. This led us to ask, does there exist an alternative space for multi-bit watermark embedding without impacting the model's prediction, so that we can get a harmless and non-ambiguous model watermarking method? Fortunately, the answer is yes. We can use the space of explanation for multi-bit watermark embeddings. Explanation is defined as human-readable reasoning behind a model's predictions. The definition might be somehow vague, and I will show a concrete example afterwards. Like other model watermarking methods, our proposed method named explanation as a watermark, EaaW, also has three stages. First, in watermark embedding stage, we use two terms in the loss function. First is the utility loss, which is the loss function used in the primitive task to preserve the functionality of the model. Second is the watermark loss. It is a hinge-like loss as follows. It can force the explanation of a specific trigger sample xt here to the explanation e to close to a watermark, specific watermark w. We use explanation here, explain here to denote the explanation function. To extract the watermark, we first conduct the explanation function to the trigger samples using the explain, and we can and then we binarize the explanation to get the final watermark. Here is W tilde, and W tilde is consists with 1 or -1 is a binary vector. So the key in our method here is how to design the function explain. In our method, we use feature attribution as the explanation to embed the watermark. Feature attribution outputs a matrix that indicates the importance of each feature in the input. Higher the importance score, the more important the features. For example, in this image, the pixel of the eagle are more important, so it will have a higher scores, but the background is less important with a lower scores. We designed the explain function based on a widely used feature attribution algorithm named LIME, and we also made some adjustments to fit watermark embedding. The first step is local sampling. We first generate some binary masks whose elements are 0 or 1. Then we mask the corresponding features in the input if the value in the mask is 0. If the value is 1, we just keep the original value. The mask features will be replaced by a certain value depending on the modality of the input. For example, we can set the pixel value to 0 as the black patch, or replace the tokens in the text data to a specific token, like UNK token, unknown token in these examples. In the second step, we input these masked samples into the model and get the predictions. Intuitively, if a more important feature is masked, the quality of the output will be significantly decreased. So we use a metric function M here to evaluate the predictions P and calculate a metric vector V. It is worth noting that the metric function can be any function which can evaluate the predictions. For example, the loss function. Since the loss function exists in most scenarios, our paradigm can be adapted to almost any task. In the third step, we take the mask matrices as X, which is generated in the first steps, and the metric vector as Y, which is generated in the second step, to fit a linear regression. The weight matrix of the linear regression is the importance scores of each features. Specifically, we use ridge regression instead of vanilla linear regression to get a more stable calculation of the importance scores. Here ends the explain function. Finally, after extract the watermark, we need to compare the extracted watermark W tilde here and the original watermark W. This problem can be formalized as a hypothesis test as follows. The null hypothesis is W tilde is independent of W, and the alternative hypothesis is W tilde has association with W. We use Pearson's chi-square test to calculate the p-value of the above task, and if the p-value is lower than a threshold, this tested model can be regarded as a stolen model. In the experiments, I briefly summarize some key findings, and you can find the complete results in our paper. Firstly, our EaaW can embed over 1,024 bits to the image classification models and over 128 bits to the text generation models. This slide shows a visualization of the trigger samples and the extracted watermarks. Here we can see that we successfully embed a watermark of a picture of AI and a barcode. This slide shows experiments about the resistance to attacks. The results demonstrate that our EaaW is resistant to common watermark removal attacks and to different types of adaptive attacks. We also compare our method with backdoor-based watermarks. We define a new matrix named harmless degree taking both trigger samples and the testing samples into account. And the results show that our EaaW is more harmless since the testing accuracy and the harmless degree is mostly higher than the backdoor watermarks. Last but not least, we evaluate our method in an important scenario named label-only scenario, where only the predicted label are accessible. So in this scenario, many information are lost, such as the prediction confidence of other classes. However, we find that we can increase the number of the mask samples in the first steps that can compensate the information loss and successfully extract the watermark. So the conclusion is our EaaW is still effective in the label-only scenario. In conclusion, in this paper, we propose a novel black box model watermarking paradigm, EaaW, to embed multi-bit watermarks into explanations. We also designed an effective watermark embedding and extraction method inspired by LIME. The method can be applied to models of various modalities and tasks. For future work, I think first, extension to other tasks and modalities such as the graph models, which is very different to other models, other tasks and models and modalities. Second, the theoretical guarantee of model watermarking is still missing in the community. For example, the watermark robustness or watermark capacity. Seeking these theoretical guarantees is also an interesting topic. Third, we can also design more effective and efficient XII-based methods for watermark embedding. I think LIME may not be the best method for all the models. We may find better methods for other modalities and scenarios. Thank you once again for listening. You can find our papers and code online and through the AR QR code. Feel free to reach out to me through emails. Thank you.
So, yeah.
For the talk, my name is Derry Wang from CSIRO's Data 61, Australia. And I have two questions for this paper. The first is, what is the rough number of inputs you need to verify a confident p-value?
Rough number
of inputs, like in the verification stage.
Number of input?
Yeah.
In our experiments, it depends on how many bits of watermark you want to embed. For example, if you embed 200 bits watermarks, we use 200 samples to do this watermark extraction and embedding.
Okay, thank you. And my second question is, have you compared with backdoor-based watermarking on the robustness? If someone temper the weights of the model, for example, slightly fine-tuning the weights, and how robust is your watermark compared to backdoor-based ones?
Unfortunately, we do not discuss our robustness with backdoor-based methods because in our paper we simply compare we think the backdoor-based methods are harmfulness and ambiguous. So we primarily compare it with the harmless degree. Yes, we simply comparison in this aspect. From these aspects, so I think backdoor-based methods is proven to be robust, and our method is also robust. I think robustness is all well, and it is all practical in practice. I think.
Yeah. Thank you very much.
Thank you. More questions?
Hi, my name is Judy from Vanderbilt University. I have two questions, or maybe just one for you. Have you tried to test your method on the model or like watermark sanitization method?
Watermark sanitization?
Yes. It's like the technique to remove any watermarking which is inserted in the model.
I this type of attacks we do not discuss in our paper. We design two adaptive attacks in these papers, such as removal attacks, overwriting attack, and unlearning attacks. So I think sanitization may be a good attack, and we will conduct it in our future work.
Yeah, I
Maybe.
think it's interesting if you can show that even with the sanitization method,
Yeah.
your watermark still robust against it.
I think it's a good suggestion. Thank you.
Yes, thank you.
So, any question? Oh, okay. I have a small question because sorry. So I think multi-bit watermarks are very meaningful because it contains more information, and even you can use this watermark to trace the model or image. So I just wondering if you consider to use some threshold to judge the ownership, like you recover exact the whole bits or some 80% is enough or something. Yeah.
Oh, I know. As I present previously, we use a hypothesis test to validate that if the extracted watermark is similar to the original watermark. If the p-value is lower than the certain threshold, like 0.01, it will be considered as a stolen model.
Okay, I see. Very interesting work. Okay, so let's show again. Yeah.